Hello, everyone. Thank you for coming. This is my passion talk on an introduction to research in computer science. If you want to follow along with the slides, I made a tiny URL. It's just tinyurl.com/passion talk research in case you want to check it out later. For those of you who want to do the attendance code, the attendance code for the portal is research paper with capital R, capital P. So just give people a second to get that. Okay, cool. Hopefully you guys got it. So hello, in case you don't know me, my name's John. I'm currently a second year computer science major here at UCLA. I'm interested in pretty much anything artificial intelligence related, especially artificial intelligence research. And I'm also currently president of ACM AI, one of ACM's other committees focused on building a community of people interested in AI at UCLA and beyond. And I'm originally from San Jose, California, where I'm currently based right now during quarantine. And the three logos that you see on the bottom right are three research labs that I've previously been involved in here at UCLA. And it's obviously, as you can tell, as a second year who's been in three labs, it's something that I really care about and something that I really enjoy doing. And I think is something that is really important and impactful. And so hopefully the goal of this talk is to convince you guys that research in computer science especially is extremely important and it's something that you might want to consider doing yourself. And hopefully you guys get something out of this talk. So just to give some quick background about what I've worked on here at UCLA Research Labs, during my freshman year, basically throughout the entirety of my freshman year, I was a undergraduate researcher in the Ozcan Research Group. I was working on a project for fast particle analysis using machine learning for quick mobile disease diagnosis. That's a big mouthful. So basically what I was doing was developing fast machine learning algorithms in order to be able to take in images of different blood samples and be able to do particle analysis. So look at things such as particle size, number of protein particles in order to do mobile disease diagnosis. We had constraints that we needed to have these algorithms be runnable on a Raspberry Pi, which is extremely hard to do. And then soon after that, I joined VCLA, also known as the Center for Vision, Cognition, Learning, and Autonomy. This is another lab at UCLA in the computer science and statistics departments. And there, I'm actually still currently working there on a project called Causal Transfer Learning for Robotics. And so basically the whole idea of this is that we're trying to build robotic agents that can learn causal relationships in environments and use this to transfer knowledge between different tasks. So just to give a concrete example of this, for instance, say you had a robot that was trained using some machine learning algorithm in order to cook a meal inside a modern American kitchen. And it was able to do this really well. And say we wanted to put this robot and put it into some like ancient Chinese kitchen, we wanted to be able to also cook a meal as well. The idea with transfer learning is that using the knowledge that you have inside the first environment, say cooking in an American kitchen, modern American kitchen, you can then learn to cook in a new environment, the new ancient Chinese kitchen, using less training time, and you'll learn faster because you have this prior knowledge. And the idea for this project is we're trying to learn causal relationships because we hypothesize that learning these causal relationships, like heat causes food to cook, is useful for transferring to different tasks quickly. And finally, a lab that I recently joined was the UCLA Vision Lab. And currently, I'm working on a project called Joint Unsupervised Learning of Optical Flow and Depth from Images, which is kind of a mouthful. So it's basically a computer vision task. And I'm going to talk a bit about this later when I talk a bit more about what exactly is computer science research. So stay tuned for that. So just a quick overview of what this talk is going to go over. There's three main sections for this talk. First is what exactly is computer science research and research more generally. Second, I'm going to talk about why research matters, why computer science research matters, and go into two stories that kind of exemplify why research in computer science is really important. And lastly, I'm going to go over why you should get involved in computer science research here as a student at UCLA and how you might want to get started and get involved in this. So hopefully this will be interesting to you. So first, what exactly is computer science research? I think to answer this question, it's important to first establish what exactly is research. So we hear this term thrown around a lot, but the essence of research is to make novel contributions that expand human knowledge. In the context of most academia, most researchers, PhD students, master students, and professors, this entails making contributions that are worthy of publication in top conferences or journals for a particular research area. So for instance, if you're interested in doing research in computer vision, there are a handful of top computer vision research conferences such as CVPR, ECCV, or ICCV. And basically when you're doing research, generally your goal is to be able to publish in one of these venues because these venues are generally peer reviewed, so reviewed by other researchers in the field. And so when you're writing these papers, you want to make them high quality because other people, your peers, are going to be looking at them and deciding if they're worthy contributions or not. So a good visualization I like to think about when I'm thinking about or explaining what exactly research is this kind of image here. So imagine this is a representation of knowledge about any field, say machine learning or operating systems or computer vision or anything else. Everything inside this black circle is everything that humans, researchers know about a particular topic. So these are things that have been published in research papers already, things that have been done at various companies in engineering. So we know what we can do and how to do it. And outside all of this white space is stuff that we don't know yet about the topic, but is knowable and something that researchers want to uncover. So when you're doing a research project, you're basically doing this. When you make a contribution, you add this little dent in the circle, and you're trying to expand into the undiscovered knowledge area. And the reason I like this visualization is because it emphasizes that a research contribution happens generally at the edge between what's known and unknown about a topic. Generally speaking, when you're doing research, you're reading other state-of-the-art research papers, a lot of the times that just recently came out, maybe a few months or weeks or years ago, and you're building on top of this knowledge, coming up with your own ideas, and then hopefully releasing your own research work as well. And this is how you're making your contribution to the knowledge that humanity has about a particular topic. And so obviously this is not something that's super wide, a giant, like most research projects don't like make the circle like really big on their own, and they don't extend super far. They're generally pretty small things that happen like right along the edge. But thankfully, there's generally, if you're working on a problem that's important and other people also think is important, there's going to be other researchers who are also working on this topic as well. And so there's going to be multiple research contributions, and over time, you're going to make the circle a lot bigger. And the cycle repeats. Once you make the circle bigger, you build off of existing research. So that's kind of just a visualization I like to think about when I'm thinking or trying to explain like what exactly is research, what exactly are we doing as researchers. In computer science specifically, there's a bunch of different areas of computer science research, from artificial intelligence, OS, architecture, networking, etc. You guys have probably noticed that a lot of these things are courses as well at UCLA, and this is a testament to the strength of computer science research at UCLA. The reason we have a lot of these courses is because there's professors here at UCLA who are doing research related to these topics. And so they have some pretty good knowledge and expertise of these things and are able to teach this at an undergraduate or graduate student's level. And so pretty much any area of CS research you can think about at UCLA, there's somebody who's probably working on it right now and is likely a leader or expert in that particular field. So I quickly wanted to go over a lot of jargon that kind of gets thrown around a lot in the research community. So one of these things is places to publish research. And you'll hear thrown around a lot terms like conferences and journals. So what exactly is the difference between conference or journal? So a conference is generally there's an in-person event, unless there's a global pandemic like COVID-19 right now, where people will go to talk about their research that they have done on a particular topic. So these things are usually events where you have to submit a paper ahead of time online usually, and then have it peer reviewed by a bunch of people. And then once you go through that peer review process, and if you wrote a good paper and did some revisions, then hopefully you get accepted, and then you get to go to this in-person event and talk about your research, present a poster. If you're one of the top papers, sometimes you get like a spotlight, like a keynote presentation, you're able to have like a really big audience there. And this is how people kind of exchange research ideas, especially in the computer science community. On the other hand, journals are periodic publications of like there's issues or volumes. You can think of them kind of like magazines or encyclopedias. And typically these papers are longer, and you still generally have to go through a peer review process. But in the computer science research community in general, people tend to consider conferences to be of higher quality and are more selective in terms of their research when compared to journals, even though there are a lot of really good computer science research journals. And the reason for this is just kind of by accident. This is just kind of how the community decided to do things, the computer science research community. If you look at other research communities in other fields like biology or physics or other STEM fields, generally speaking, people tend to think of journals as higher quality research contributions than conference papers. And another thing I forgot to mention, generally speaking, after a conference is over, there is usually a collection of all the papers that are made in the conference that are released. And this is called the conference proceedings. So if you ever, for instance, there's a conference in AI called NeurIPS, and sometimes you'll see that if you look at like a CV of a researcher, it will say like this paper was in the proceedings of the 35th annual conference on NeurIPS or whatever. So that's what it means. So this means that it was accepted to a particular conference. Another thing I wanted to go over are different kind of flavors of computer science research. So there's a delineation between theoretical research and empirical research. So in theoretical research, generally speaking, in CS, you're trying to prove rigorously your results. So maybe you come up with a new sorting algorithm and you want to write about it in your paper. Generally for theoretical research, you want to prove its time and space complexity rigorously. And usually this implies that there's a lot of math involved. So a lot of the times, if you read theoretical computer science papers, it will actually kind of look like a math research paper because there's like no code, there's no mention of them actually running the algorithm like empirically on a real computer. So there's a lot of overlap in math and computer science research when it comes to theoretical research. On the other hand, there's empirical research. And so when people are doing empirical research, generally they're basing success of their new research ideas based on some kind of experimental evaluation. So you'll run some experiments and say, if you get certain performance, then you say, okay, this was like a reasonable or a valuable research contribution. So for example, if you're doing empirical research for like a sorting algorithm, maybe you have some kind of heuristic that you added to your sorting algorithm for your particular problem, and you run it on some benchmarks, and it got like 50% better than every other algorithm that was currently being proposed for this particular problem. But you haven't been able to theoretically prove that this search algorithm is a lot better or is actually faster asymptotically or in terms of time complexity and space complexity than any other algorithm. This would fall under empirical research. And so most applied research, this is something I'm going to go over a bit later, will fall under the umbrella of empirical research. So research that you see a lot more in industry. So just to give a quick example of theoretical research. So don't worry too much about reading the entire abstract of this paper, but I just wanted you to focus on this particular segment. So this is a research paper trying to prove a particular property of neural networks, and basically they're saying that we show that a neural network with a feed-forward neural network with a single hidden layer is able to, with arbitrary precision, approximate any function. So that's all they're trying to show. So they're just trying to show that neural networks have this certain property, and they do a bunch of math in this paper in order to prove that. But they don't have any kind of experiments that they're doing. They're not trying to come up with a new algorithm. They're not running any algorithm on any data or anything like that. They're just trying to prove specific properties of algorithms or data structures that we might be interested in. So this would be an example of theoretical computer science research. An example of empirical research is AlphaGo, something many of you have probably heard of in the past few years. So I think back in 2015, DeepMind, a subsidiary that was acquired by Google, basically wrote a program that was able to beat the world champion in the game of Go, which is this territorial game on this 19 by 19 board. It's a pretty simple game in terms of the rules. It's just you place a stone on the board, you take turns, you try to capture as much territory as possible. But because of the size of the game, there's actually more configurations of the board than there are atoms in the observable universe. So you can't just exhaustively search all the possible board configurations to decide what kind of move you want to do next. And so basically, what these researchers did was they used some machine learning methods with some combined with some tree search methods in order to try to beat professional players in Go. And so I want you to just look at this particular segment of the abstract. So basically, they say they achieved a 99.8% winning rate against other Go programs, so other AIs that were made by other organizations, and defeated the European champion, as well as Lisa Dole later on, who was considered the best player at the time. And if you actually go through this paper, they never actually prove that their algorithm is the best particular Go algorithm, or even prove that it's better than any other algorithm. The entire basis of whether or not the research were successful or valuable contribution was based on a benchmark, so being able to win against other Go programs and professionals. So they're just trying to look at the results of their experiments in order to evaluate whether their research was good or not, and that's how they judge success. So that's kind of the delineation between theoretical and empirical research. Another delineation that doesn't necessarily fall under empirical or theoretical that you might hear a lot about is a delineation between basic research and applied research. So basic research is research with the intention that you're trying to make novel contributions in a field, but you're not worried about making an immediate or direct real-world impact. And so this research can be either theoretical or empirical. And generally speaking, you'll find this a lot more common in academia, so in university research environments. And the simple reason for this is because a lot of companies don't see basic research as valuable to their bottom line, so they don't do it. But at least in artificial intelligence research specifically, a lot of the big companies, the big AI labs, Google, Facebook, Amazon, etc., are actually hiring a lot of people and allowing their research scientists to work a lot more on basic research problems that may not actually have any impact on any product for many years down the line. And the reason for this is just that it's really hard to predict what will happen in AI. So a lot of basic research might end up being really valuable. And I'll give you guys an example of this a bit later. So on the flip side, applied research is research that's focused on applying existing research to real problems, so usually for a product. So you'll often hear a term get thrown around when you're talking about different teams in a tech company. So research and development companies or research and development teams in companies are essentially people in a company that are doing applied research. So they're trying to look at existing research and seeing how they can fit that into the company's product objectives and see if they can make things better with this new research. And almost always, applied research is empirical research. They don't really care about proving that their new algorithm that they're going to use for their particular search is going to maybe be theoretically better than any other algorithm. They care about the bottom line, right? The actual performance, the benchmarks on real world data and real use cases. And so generally, it's almost always empirical research. And you'll see applied research actually both in academia and in industry. So I guess kind of the one example is the lab that I was working in freshman year that I mentioned earlier. This would fall more under applied research, even though it's in academia, because we're trying to apply a lot of machine learning stuff to biological problems. So you can see it in both academia and in industry. So just to give a quick example of basic research, this is a example of research that's actually coming from a PhD student I currently work with in the VCLA lab. So basically, the idea is they're trying to solve this toy problem. So basically, you have a robot in a virtual escape room, and it needs to press different levers in order to be able to press the green button and open the door and escape the escape room. And there's a causal structure related to each of these rooms. And so essentially they're trying to learn causal structure or causal relationships as fast as possible and use this in order to transfer between different escape rooms with similar causal structures. And so notice that this particular escape room, one, it's virtual. There's no actual real escape room like this in the real world. And very likely there's never going to be a real escape room like this in the real world that we would actually care about solving or opening, because there's not really a real use for this. But the point is, this is basic research because it's still a valuable problem to look at when we're trying to develop algorithms that maybe one day might be useful for more complicated problems. So a lot of the times we have a lot of these toy problems that we would never actually do in the real world because we want to see if algorithms would be able to exhibit certain properties. And hopefully if we're able to solve these toy problems, we're able to move them to more applicable, more complex problems. So this is an example of basic research. This is not like a product or anything close to it. On the other hand, here's an example of applied research. So this is a research paper coming out of Facebook AI Research, also known as FAIR. And it's basically talking about its new applied reinforcement learning platform. For those of you who are unfamiliar, reinforcement learning is just a type of machine learning that's concerned with acting optimally inside any particular environment. So you can define the environment or the agent that's acting in this environment to be really anything. And so an example they give is the environments of Facebook notifications. So in this paper, they talk about how they deployed a new reinforcement learning algorithm in order to actually serve notifications on Facebook. And basically in the paper, they talk about how it was beating previous methods that they were doing, and they were trying to implement methods that were presented in research papers from basic research products. And they were able to actually perform a lot better. And now this is actually the system being used to serve you guys notifications right now in Facebook. So this is an example of applied research. It's trying to do something directly with the intention of being applied to a product that's actually maybe user-facing. So another thing to kind of clear up when we're talking about research is what exactly is a research lab? So a research lab is just a group of people who are producing research contributions in a specific research area. And a lot of the times this is also called a research group. And typically there is between 5 and 25 members in any research lab. And this goes for both labs at universities like UCLA and at big companies as well. So an academic lab generally has this structure. There's a principal investigator, also known as a PI. And this is a professor who leads the lab and advises graduate students. You can think of this as analogous to a CEO of a company, if you want to think of the academic lab as a company. Additionally, a lab may or may not have affiliate professors. So these are other professors who lead projects and advise graduate students. And you can think of this as analogous to an executive board of a company. And lastly, there's grad students, so PhD and master students, who are the people who do the bulk of the research work. And you can think of these people as analogous to employees of a company. By contrast, an industry research lab has a slightly different structure. Generally speaking, there's a lab director, you can think of as a PI as well, who leads the lab, but in addition doesn't really have as much freedom and has to report to someone higher in the company hierarchy. Under the lab director, generally there's research scientists, so people who do the bulk of the research work, and a lot of the times these people are hired directly after completing their PhDs. And lastly, something that most labs don't have in academia are research or software engineers. So these are people who build tools to support research scientists, build different infrastructure to help them run their experiments and actually evaluate a lot of the contributions that they're making on real world problems. So just to compare the two lab structures, in academic labs, the professor generally has basically complete control to do whatever the professor wants to do, especially once the professor's tenured. There's really almost nothing that can be done to fire the professor in terms of what they work on. And by contrast, lab directors in industry labs must make sure projects have some kind of application within a few years. Secondly, is funding. In academic labs, funding mostly comes from grants. And a lot of these times, the grants can also come from companies as well, in the case of computer science research. So a lot of the big companies, Google, Facebook, Amazon, actually fund a lot of computer science research in universities. You guys might have seen this in like newsletters, I think from the engineering computer science department, of various professors getting really prestigious grants from a lot of these big companies. In industry labs, obviously the funding comes um, from the company itself. One big distinction between the people in academic and industry labs is that the people who do research in industry labs typically have already gotten a PhD or some other graduate level degree, so they already have a lot of experience doing research before. Whereas in academic labs, a lot of these researchers are currently doing their PhDs, so they're currently getting their first few experiences in research. And lastly, one big thing to distinguish between the two is that academic labs, all the engineering and research work is done by grad students, whereas there's a bunch of different software engineers who can assist people doing research in industry labs. They also have a lot more access to compute and software engineers as well. So just to give you a quick idea of what kind of companies have research labs, pretty much if you look at any of the big N, Amazon, Google, Facebook, etc., they all hire PhDs, they hire research scientists to do research, both actually basic and applied research, especially in artificial intelligence, but a lot of the even smaller companies, quote unquote, so not the big N like Lyft and Uber, actually have their own AI labs because they see a lot of value in AI in terms of like self-driving that they want to do, as well as a lot of different targeted stuff for their users. And so pretty much if you look at any big company, they're going to have research labs. And now there's kind of a trend that a lot of smaller companies and startups are also hiring a lot of research scientists and having their own labs because they see the value in having this at least applied research in the long term is really valuable. So I know that was a lot of different terms. So I kind of wanted to give a concrete example using all of these terms through my own experiences at the UCLA Vision Lab. So I'm currently working in the UCLA Vision Lab. It's in the computer science department. So it's at UCLA. It's an academic research lab. And we do research in computer vision and artificial intelligence. And the principal investigator is a professor of computer science named Stefano Salvato. Just briefly before I talk about what exactly I work on and whether that falls under the different research categories, just a brief aside of machine learning in case you guys are unfamiliar. So machine learning is a kind of artificial intelligence, basically trying to learn how to perform a task rather than being explicitly told how to do it. So generally speaking, this involves specifying some kind of objective function, and then the algorithm will optimize this objective function. Oftentimes this will be called a loss, and we would want to minimize the loss. So there's two kind of main subsets of ML. There's supervised learning, where you're given a bunch of inputs and outputs, and you're trying to map from the inputs to the outputs. And there's also unsupervised learning, where you're given just data and you're trying to learn patterns from that data without labels. One particular task in computer vision we're interested in is doing depth prediction. So given an image, for every pixel, we want to predict the distance from the camera to the object at that pixel. So you might take in an input that's height by width by 3. So the height by width is the size of the image, by 3 because there's RGB channels, and you're trying to output height by width by 1. So for every pixel, there's just a single number that represents how far away it is from the camera. And this is typically done using supervised learning. So given you go out and collect a lot of this data, maybe you have a LiDAR, and you're just taking these pictures and you're capturing how far away all these objects are. And one of the big challenges with this is that LiDARs are extremely expensive. They cost tens of thousands of dollars. And you might imagine that using depth prediction is extremely helpful in tasks such as doing self-driving cars. And so if we want to build self-driving cars that most consumers can buy, adding on additional costs that are tens of thousands of dollars is not a great way to sell them to people. So we kind of want to go away from using LiDAR if we possibly can. Another task we might be interested in, especially for self-driving, is optical flow. And so what optical flow is, we're trying to, for every pixel in an image, so you're given two images at two different times. of the same scene, basically. And for every single pixel, you want to predict a vector of that pixel's movement from the first image to the second image. So just to give an example of this, if you have a car at location 0, 0 in image at time 1, and at image in time 2, that car is now at pixel location 1, 1. For pixel location 0, 0 in your output, you would want to output 1, 1, which is a vector representing the 2D movement of that pixel in the image. And so this is why the output would be height by width by 2. And similarly to depth prediction, it would also be done typically using supervised learning. And you can imagine this is extremely, extremely, extremely annoying because there's no hardware that lets you do this really easily. You need a human to go in and manually annotate every single pixel for every single pair of frames that you have in order to be able to have these input-output pairs that you can feed into your machine learning algorithm to hopefully learn. So we kind of want to get away from this because this is really annoying and really, really tedious and really costly too. So what we're working on is we're trying to, with a single neural network, be able to jointly learn depth and optical flow prediction in an unsupervised way. And so I'm not going to get too much into the specifics of how we're doing this, but if you're curious, the way we're trying to do this is obviously using deep neural networks, but we're trying to do this without labels. And the way we're doing this is basically by cleverly designing the neural network in various ways in order to exploit geometry, and also design loss functions that kind of exploit geometry, because when you predict optical flow and depth, these are related tasks. And you can do some reconstruction with like some camera matrices and some complicated math stuff in order to reconstruct different things. So there should be some consistency between these two outputs that you can have in a loss function in order to help you train it in an unsupervised way. I know that's not super clear explanation, but if you have questions later on, I can go in more in depth if that's helpful. And so basically what we're trying to do is we're trying to beat performance of previous methods on various benchmarks. So there's a lot of data sets out there on optical flow and depth. And so we want to develop an algorithm that beats these other supervised methods and beats other previous unsupervised methods as well. And so that's why this would be categorized as empirical research. That's simply because we're trying to do well on a performance metric, and we're not trying to prove that our particular algorithm rigorously and mathematically is better than any other neural network. And lastly, our main goal is to publish in a conference paper, so one of the top computer vision conferences ideally. And so this would have us basically be under basic research, because we're not trying to apply this to a product or anything like that. And so you can actually imagine that this particular research project in another context, maybe if done in an industry lab, might actually be applied research if they were planning on actually, after this research project being completed, put it into, say, an actual self-driving car. That would be more of an applied research project. But we're not trying to do that, so that's why it's basic research. So hopefully that kind of gives more of a concrete idea of what a lot of these terms and jargon means in computer science research. So why does computer science research matter? Hopefully you guys have a better understanding of what computer science research is. And now I'm going to try to convince you that it's actually really important. And one of the obvious big reasons is high impact. And I know as UCLA students, especially if you're in computer science, you get constantly told by the department we're the birthplace of the internet, and the research was done here. And so I didn't want to bore you with that story, because obviously that's really highly impactful, but it's also just really obvious and kind of boring. So I'll tell you a different story about why research is really impactful, something that you definitely know about, but maybe don't know the full story about. So I'll tell you about a typical tech startup origin story. So for those of you who are unfamiliar, this is Larry Page and Sergey Brin in a garage somewhere, probably in Mountain View or Palo Alto, when they were building Google. And so everyone basically uses Google. And so basically the cliche tech startup origin story kind of looks like this. You come up with some idea, like a search engine. Maybe hopefully you're the first one. And then you drop out of college. It's probably like Stanford or something. Get some VC funding. Google got funding from Kleiner, one of the big Silicon Valley VC firms. And then you just move fast and break things, beep, bop, boop. And then all of a sudden you have $1 billion valuation. And then you IPO and you have stocks. Now you're like a billionaire. And so a lot of people really emphasize the early stuff, like coming up with the idea. People think that that's like really important. Like you just have to come up with your idea, be first, and just go as fast as you can, and work just really hard and not really think too much about the details like in the middle. Um, but a lot of people assume that Google, because they were also something that was kind of following this kind of timeline, has a lot of similarities with that kind of cliche um, idea of what a tech startup origin story might look like. But one of the big things that's important to note was that Google was not actually the first search engine. They weren't the first to come up with this idea. So back in 1990, there was a one of the first few web search tools called Archie Query Form. Yahoo, a really big player, also came out of Stanford students, came out in 1994. Ask Jeeves, now called Ask.com, came out in 1996. And right before 1998, MSN search, which later became Bing, came out actually before Google, which only then came out in 1998. So a lot of the times people are like, oh, having a first mover advantage is like one of the biggest, most crucial things, or just having a really good idea is one of the biggest, most crucial things for having a really successful startup. But this actually didn't turn out to be the case for Google. And so why exactly did Google win? We all know now that we don't even think about using any of these other search engines. It's almost laughable. It's like a joke when you say that you want to Bing something. We've used Google so much that we call it Googling something now. So why exactly do Google win? Um, and unsurprisingly, I'm going to tell you that one of the big reasons was research. So in 1998, Larry Page and Sergey Brin were actually currently PhD students, computer science PhD students at Stanford, and they were doing research that was related to a lot of search or a lot of web search stuff. And so they came up with this algorithm called PageRank that was able to basically better provide search results and rank web pages given various search queries. And this research was way faster, way more efficient than all of their competitors, led to better and faster search results than everyone else. And so when people started using Google, they're like, wow, my search results are so much better. I'm actually finding things I want to find in comparison to all of the other search engines out there. And that's why they took so much market share and were able to basically dominate the market. Everybody started using Google because they would actually be able to find stuff there. And eventually the competition either died out or they moved into other areas, like Microsoft basically became known for just like their Windows OS. And so they didn't really have to do as much work as they maybe have needed if they didn't have this really fast search algorithm. And actually to this day, PageRank is still one of the criterion, one of the core components of Google's search algorithm where they use to rank various search results. Obviously, there's a lot more complicated stuff they added onto that. And but a lot of that actually comes from research as well. So to this day, PageRank is actually still highly like influential. And maybe without this research, Google may not have been as successful as they were. And it's likely they actually probably would not have been as successful because it's not like Yahoo and MSN and Ask.com engineers were like really dumb people or anything. They knew what they were doing. They were good engineers, so they just didn't have this cutting edge research that helped them actually pull through and have better results. Another big reason why computer science research matters is freedom to work on long-term projects. So many of you guys are probably familiar with the deep learning revolution that came around in the 2010s. We hear about it all the time. It's a big buzzword. So deep learning is being used for everything, computer vision, natural language processing, etc. But the interesting thing is that research on neural networks actually came long before any of the current deep learning revolution that we see nowadays. So if you look at the top paper, this is a paper talking about the perceptron. And a neural network is just a multi-layer perceptron. So it's multiple perceptrons stacked on top of each other. And this paper actually came out in 1958, long before we had any of the neural network advances that we have today. And similarly, another paper that went over convolutional neural networks, which are now the basis of pretty much all state-of-the-art computer vision algorithms, was actually introduced in a paper in 1998. And so a lot of these researchers were basically told at the time, oh, you're not working on anything practical. It's never going to be useful. You should just like quit and work on something else. but they didn't. They kept working on this stuff, and they still published their papers. They got good results. And basically what both of these papers found was that for a lot of simple problems, like predicting the handwritten digit or text from an image, that these methods were actually really good. So if you actually have ever seen the MNIST demos, this is the paper where the MNIST dataset was actually created and used. They found that convolutional neural networks were really effective for this, but they weren't super effective for other more complicated problems. And in hindsight, the reason was just that we didn't have the computing power that we have today. And so basically when the 2010s came around, we had a lot more computational power and we're able to actually use these algorithms, and they turned out to be way better than anything that we actually had before. And so I guess the point I want to make is that, without the freedom to work on long-term projects that might not pan out immediately, without the freedom to work on basic research, it's likely these papers would have never been created, right? If people didn't think it was valuable, universities wouldn't fund this research, companies wouldn't fund this research, people wouldn't even want to do a PhD to try to study these problems at all, because why would you do that? It's not applicable. But I think in reality, it's really important to actually have the freedom and give people the ability to work on problems that might not turn into a product anytime soon, but are still really important questions to delve into. And if we didn't have this kind of investment in this kind of basic research, it's likely these papers would have never been made at that time. And the advances and benefits, immense benefits that we see now from deep learning probably wouldn't have happened for a very long time. And it's unlikely that if in a world where we didn't fund basic research, that a company would all of a sudden do this kind of research work, right? And so who knows how longer it might have taken to do this kind of stuff. And so that's just another example of why I think doing computer science research is extremely valuable. So hopefully I've been able to convince you that computer science research is valuable, and hopefully you have a better idea of what computer science research might look like. So why should you get involved, and maybe how can you get involved if you're interested? One of the biggest reasons is that you're currently at a world-class research university right now. So at UCLA, we have a ton of amazing professors and grad students doing tons of state-of-the-art world-class research. And if you're not planning on doing grad school at all, then this is the last time you're gonna ever be at a university. You're gonna be here for 4 years. And once you leave, you're probably never gonna be able to have this opportunity ever again. And that's simply because you'll be busy with life, maybe you have kids, you'll have an actual job. And even if you somehow were able to go around all of those obstacles and you decided to apply to the lab anyways, they're probably gonna say no because you're not a student and they wanna focus on the current student body right now to give them experiences. So while you're here for 4 years, you should take advantage of that. The fact that you have these professors here and have this opportunity, even if you're maybe leaning towards not doing research, I would say that just do it at least one time, because you never know, you might really enjoy it. And you don't want to look back and say, maybe I wanted to try that and have this kind of freedom in what I work on later on, when you don't have the opportunity to go back and do that. In UCLA computer science alone, we have actually 31 research labs, which is quite a lot, and 38 professors who are doing research just in the computer science department alone. And we have almost 400 CS graduate students. So there's something, I think, pretty much for everyone. We do computer science research in pretty much every field, and there's professors and grad students who are working on it. So hopefully something, at least in the computer science department, is interesting to you and something that you might want to look into. In addition, there's a ton of other research labs outside of the computer science department that need people with computer science skills to help them with doing a lot of experiment work, data processing and analysis stuff, because they don't simply have the manpower that have the technical expertise that you might have. And so there's even a lot more opportunities outside of the UCLA computer science department as well. This kind of segues into another reason why I think it's important, or you might want to do research, is that you'll actually gain a lot more software engineering experience than you might have realized. So as a person working in a research lab, it's highly likely, if you're a person with computer science skills, that you'll have to write a lot of code to run your experiments, assuming obviously you're not doing purely theoretical research. You'll want to evaluate new algorithms you're trying, or maybe if you're in another in a lab outside of computer science, maybe you want to analyze a lot of the data that came from their experiments. And additionally, other people will also want to use your research for their research, right? So a lot of researchers publish their code on GitHub publicly when they release their papers publicly. And so the whole point of this is that other researchers can use their work and not have to reinvent the wheel in order to build off of what you've already done in order to advance research faster. And so you'll actually gain a lot of experience in actually having to maintain code as well. I know right now, currently, that I'm in a lab in VCLA. I've worked on a tool called VRGen, and this is a Unreal Engine environment for basically running a lot of robot machine learning experiments virtually. And we've kind of open sourced like early versions of it, and people have gone to us and talked about um, like things they might want to see changed and issues that they're having. And I know a lot of the grad students that are working on it have gained a lot of experience in terms of maintaining the code and actually listening to their users as well. And hopefully through all of this, you gain a lot of resume-worthy experience for software engineering roles. So maybe you join the lab and you decide maybe research isn't for you. That's totally fine. You'll actually still gain a lot of reasonable experience for software engineering roles as well. And so you shouldn't feel like you're going to be wasting your time by doing this research. There's a lot of interesting work that's being used. A lot of research labs use all the same tools that a lot of software engineers use as well. And so you gain a lot of experience that's hopefully valuable no matter what you decide to do after you join the lab. Another big reason, probably the most important reason why you might want to do research is having high freedom. So as a researcher, you're going to be able to decide what research questions and problems are interesting for you to work on. You get to decide how you want to solve these problems, and you don't have to worry about making some immediate direct impact on some product application. So you can imagine if you were in a company doing a typical engineering job or any other typical office job, you generally don't have any of these freedoms, right? You don't get to decide what's an interesting question to look into. You don't get to decide what to work on. Usually your boss tells you that. And a lot of the times they'll even tell you how to do your job. You have to use specific workflows or tools. You don't get to do a lot of experimenting about how you want to solve your immediate problems. So if you're someone who really values being able to work on something that you think is really impactful for you or really meaningful for you, doing research is a great way to do that, especially when you don't have to worry about the bottom line of a company that you might be working for. Another big reason to do research is if you're interested in artificial intelligence. So I can talk about this a lot because I obviously spend a lot of time doing stuff in artificial intelligence. And just from looking into the field of artificial intelligence right now, the vast majority of the really interesting and big contributions that are happening in artificial intelligence are coming out of research labs, both in academia and in industry. So typically the people making the big advances, the really cool stuff, are people with PhDs who are doing research, releasing papers, even for applied and basic research. So one thing to think about is that you're right now at UCLA, and I mentioned that earlier. UCLA is pretty good in terms of computer science research. We're also pretty good, I think, in terms of AI and machine learning research as well. So this is a graph of papers accepted to NeurIPS in 2019. So this is Neural Information Processing Systems. It's one of probably the top two most prestigious conferences in artificial intelligence and machine learning. And this is a list of different institutions that basically published the most papers, had the most contributions at the conference, and UCLA is pretty high up there. There's a lot of other institutions that are like not on this graph, like actually hundreds. So we're one of the top institutions that publishes really good artificial intelligence research. And if you're interested in artificial intelligence, there's a lot of really amazing professors that are here. So definitely you should take advantage of that and just like try to talk to them and try to get in their lab if that's something that's interesting you might want to work on. And very recently, UCLA actually has been on a big hiring spree for AI professors. In the just past 2 years alone, I think there's been like 4 professors who have been hired working on machine learning, which is like pretty unheard of. Like professors get hired pretty slowly. Like a lot of the times the department might hire like 1 or 2 professors every year. And a lot of the times they'll be working on other things that are not machine learning. So there's a really big push at UCLA to bring more artificial intelligence research here to UCLA. So it's expected to grow more in the next coming years as well. So if you're interested in AI, And this is something that you should definitely look into while you're here at UCLA. Another stat that might be interesting to look at is just the fact that AI is blowing up. AI research is blowing up just generally, like right now, a lot. And if you look at the graph of papers that have been submitted, there's a lot more interest. It's almost like exponential growth. And this is because a lot of research is being funded. A lot of companies like Google AI or Google, Facebook, and Amazon are actually funding research in academia as well as doing research on their own, hiring a ton of research scientists in order to publish papers in these top conferences as well. So there's a lot of investments going into this. And for AI, it's likely not going to go away because having like intelligent computers is going to be really valuable. And I think this growth is gonna continue, maybe not at the same rate, but it's likely that you won't have to be really worried about job security if you're at least in AI research. So another reason why you might be interested in doing research if you're interested in AI is that there's obviously a lot of really cool stuff and investment going on in the AI world. So a lot of AI researchers are making a lot of money doing this. Obviously, you should be passionate about what you're doing, but if you're really concerned about making a living, I would say that at least for AI research, there's a lot of money to be made from it. Because I know there's a kind of a misconception that a lot of researchers are poor because they just work like on research that is not super equitable. But a lot of these big companies are recognizing the value of this research work and are paying like their research scientists actually quite a lot. So if money was a big concern for you, I would say don't worry about it if it's at least within AI research. Some other things to consider is that there's obviously a lot of really cool stuff being done with artificial intelligence. So for instance, DeepMind, which is a subsidiary of Google, was able to use AI to reduce their cooling in their servers by over 40% by just employing a artificial intelligence algorithm. And this is massive, right? Because Google data centers process all of the user, billions of like searches every single day. And so reducing the cost of cooling all of these data centers is actually really huge, and actually helps a lot with the environment as well because we're reducing emissions that are being created from doing this cooling. Some other interesting stuff, obviously self-driving cars are somewhere on the horizon. A lot of companies like Waymo are actually hiring research scientists in order to work on self-driving technology. You need people to do perception for these new technologies that are being introduced. Um, there's a lot of interesting creative stuff also being done with AI. So OpenAI, which is a nonprofit doing artificial intelligence research, recently created a bot that actually makes pretty interesting sounding music, I would say, by just looking at a bunch of music that's been made in the past. And so there's actually a lot of really creative endeavors that intersect with artificial intelligence as well. And a lot of this stuff is being done in research labs across the country, not just in companies like OpenAI. If you're interested in doing improving like health outcomes for a lot of people, there's a lot of really interesting work being done at the intersection of artificial intelligence and health. An example of this is that artificial intelligence is really good now at looking at images of things and just doing different classifications and diagnosis. So AI is becoming pretty competitive with a lot of human radiologists for screening X-rays for diseases, for instance. And another example, if you're interested in AI that's able to maybe communicate with humans and through natural language, be able to talk to them. Over the past, I think, 2 years, Google has been developing and releasing a system that's able to mimic humans. So you can tell your phone in order to maybe book you a reservation at a restaurant, and it will sound just like a human and be able to have very basic conversations with the person on the other end. So these are just a bunch of really cool examples of really interesting stuff that's come straight out of research labs that research scientists have worked on. And so if you're interested in any of these things, I would say going into AI research is a really good reason to do that. So these are a lot of examples of things that AI was able to solve. But I think another great reason to actually go into AI research is that there's a lot of problems right now with current AI systems, and a lot of them have to have a lot of social implications and impact. And so I think they would be interesting to you as well. So for instance, recently Amazon tried to build an AI tool in order to hire people But basically it found that it was discriminating against women. And so they basically shut down the project. And so this is a project that was coming straight out of an Amazon AI research lab. They were trying to basically automate their hiring processes a lot more. And so there's a lot of examples of this where AI and a lot of early research work is being put directly into real world use cases. And thankfully, this time it wasn't put out publicly. They found out the problems before they actually started using this. But sometimes research scientists are not so careful. So 2 years ago, Google released basically their computer vision technology, and this computer vision technology basically classified Black people as gorillas, and this is extremely problematic. And so, if you're interested in making AI, making sure that it's accessible and actually benefits like all of humanity, we need more and more people to work on this who actually care about the ethics and the social implications of a lot of these algorithms. As a UCLA student myself, I would like to think that most UCLA students are people who care about these issues and want to actually improve and make sure that technology is useful and helpful for all of humanity. So hopefully, if this is something that's interesting to you, both AI and the impacts that it can have and negative impacts that it might have, and how we can actually solve these problems, going into AI research is one of the greatest ways in order to do this. Because increasingly, a lot of this technology is coming straight out of research labs into our pockets, into our phones, into our everyday lives without us knowing this. So it's really important that the people behind these technologies really care about these implications and the ethics of what they're building. Another thing to think about is AI is being used a lot in a lot of countries and a lot of organizations that don't care that much about ethics. So a lot of dictatorships out there in the world are building autonomous weapons in order to target people. And there's a lot of implications that this has. For instance, if a robot AI decides to pull the trigger and kill somebody, who exactly is responsible? How do we deal about that? We need a lot of people to work on this problem and to think about these issues and how we can solve them. AI is also being used in the criminal justice system now in the United States. People have actually been sent to jail for AI systems that haven't been tested for bias. So a lot of these systems are being used, for instance, for recidivism prediction, so predicting how likely someone is to go back to jail after being released. And these systems are using historical data, and this historical data inherently has a lot of different biases in it. And the people that built this software didn't really consider this that much. And so it was sending disproportionately Black people to jail, Latinos to jail more often than other people unfairly because it was using really biased data. And so we need people who are working on AI systems with these kind of implications to understand the different biases that might exist in this data and how to actually like improve this, right? Because we don't want this like affecting like us in the real world. And I think recently UCLA also had like a town hall on use of facial recognition. And there's obviously a lot of problems about that, and we need people to be thinking about this issue as well. This is a really this is actually used a lot in dictatorships, such as like in China, where they're using facial recognition in order to help assist with their like social credit system and to basically track the movements of all their citizens. And if we're not careful about who's actually working on these technologies here in the United States or at other places where there's democracy, there's going to be like pretty huge problems because people are going to a lot of the time suggest that we use AI for a lot of these really 1984 Big Brother like applications. And it's important that we have people who are thinking about these issues, who actually care about the ethics and implications for just ordinary people, for everyone, and not just for the majority of people. So hopefully I've convinced you that there's a lot of really interesting applications and things to do in AI, as well as just in computer science research generally. So how do I get involved if I have actually convinced you? So first, you obviously want to find a lab. And so one of the things to think about is whether you're interested in theoretical or empirical research, or maybe basic or applied research. And this can kind of guide and filter the different research projects and areas that you might be interested in working on. Additionally, most research labs also have a website listing leadership, people, research areas, and publications that they work on. And so if you just Google search a topic you're interested in plus UCLA lab, this is probably the best way to find a lab. You just look through their website. I would say that the undergraduate research portal that UCLA provides is actually pretty bad. It's like actually really, really, really bad, especially if you're computer science research. It's not really super helpful because most labs don't actually post there. They don't really have any incentive to. Most of them just put in the effort to put their information on the website. So if you go looking out for that, that's the best way to find a lab. So once you do find like a bunch of labs that you're interested in, you should like skim through the website and like look at papers to see if the problem that the lab is trying to solve is something that's like interesting to you. You don't have to like really understand the papers super in depth. I think the biggest thing is that you want to show that you're passionate and actually care about the problem they're trying to solve, and you should be fine. They're not expecting you to like understand the different solution methods that they're trying to implement, because obviously these are really complex things that graduate students have spent countless hours, years working on, trying to formulate. And just a quick plug, ACM AI actually did a workshop on research position search and internship search, specifically for AI positions. So if you're interested in AI specifically, I've linked the YouTube video to that workshop if you want to look at it later. So once you've already found labs that you're interested in, how do you actually join one? So after you maybe read through the lab website, you would want to look for instructions for contacting people about joining the lab. And so a lot of the times, if you look at these lab websites, they say, oh, if you're interested in these projects, you should contact X, Y, and Z grad students. Or maybe if you're interested in this project, you should contact this professor. Or if you're interested in joining the lab, you should contact the principal investigator. And so if those instructions exist, then you should obviously follow those instructions. Otherwise, generally speaking, it's totally fine just to contact the principal investigator, which should be listed on the lab website, usually just by email. All you have to really do is send a short email indicating your interest. You want to generally include your resume as well with your relevant coursework and experiences. And in terms of the application process for most labs, it's usually pretty informal when compared to most other technical jobs. But one common thing is that there's usually one interview to kind of gauge sometimes your technical ability and sometimes just your interest in the project. A lot of the times, labs will ask you to complete like a simple, short project, or to read through some papers, or to work with the lab on a small project for a bit before officially joining the lab. So it varies quite a lot between different labs, but generally the process is not super formal. So you shouldn't be super worried about getting in or being rejected from the lab. Generally speaking, if you show the effort and the interest, you should be fine. And so a question I get a lot is, what might you actually work on as an undergraduate student in a lab? So there's a lot of different answers to this, and it can vary a lot between different labs. But for students with computer science skills, generally one thing that's common for all undergrads in a lab is you're going to be doing some sort of software development at least. So you'll be running experiments on code. You'll be building tools to help support their research, different infrastructure, running maybe machine learning code on the servers they have, and maybe running new algorithms that they're trying to implement and see if they're actually better. In addition, you might also, it's very likely you'll also be reading research papers on related work to the lab. So work that's been published by members of the lab previously, and also work that's been published by other labs at other universities or companies that are related to whatever you're doing. And then on top of that, sometimes the grad students that you're working with will ask you to also help them ideate as well. So come up with new solutions to actually be involved in the research process as well and work on implementing these solutions, maybe either in code or if it's like theoretical research, like working on the proofs and stuff. And so once you're able to do this, a lot of the times, if you actually are successful in making your research contributions, you can write or publish your research in posters or papers or conferences or journals. And so this is kind of the broad spectrum or range of things that you might be working on as an undergraduate in the research lab. By contrast to um, graduate students will be most focused on basically the last three bullet points. So doing the research paper stuff, implementing solutions, and like trying to write papers for conferences. If they do have you in the lab, because generally speaking, they'll offload more of the software development work onto interns or undergrads if they're able to. And that's just simply because when you're getting started, your skill set is more suited for those kind of tasks. But later on, once you get more involved in the lab and are able to understand more material from coursework you're taking, or once you're able to read more research papers, then you'll be able to do more of the stuff in the second to fourth bullet points a lot more. And you'll be able to almost be considered as an equal in the lab in many regards as to the grad students. And yeah, that's pretty much it. I hope you guys found that interesting and helpful. And thank you for coming, of course. This is something I'm really passionate about. And if you have any questions, I would love to answer them. And please fill out the feedback form at this link to help the Passion Talks organizers make these events as best they can be in the future. So thank you. Do we have any questions from anyone?